Yeah. Okay. Hi. Yeah. Okay. So thanks, Angel. Thanks, Valdemar, Juan Pablo, for the invitation. So I will talk about some old results of mine about some compactifications. In general, when we have some manifold, and if this manifold has some geometry or some property or some object on it, we would like to compactify the manifold because we understand better compact manifolds. And we might try to compactify it while preserving this object, this geometry. So the object I will be thinking about is actions. So that's what the words mean. So suppose you're given some non-compact complex manifold, M, and suppose that it has an action of some complex Lie group, holomorphic action acting transitively. So you may ask, can we compactify this manifold while preserving the action? If yes, in how many ways? Of course, this is a very, very general question, even in this restricted setting of complex manifolds. And there have been works by Lescure and Huckleberry and Olje-Klaus dealing with this situation, probably more general compactifications in small dimension, but in some sense, the first case they left open is the case of dimension 3, especially this case. Our setting, this will be our setting, that of Kleinian groups. Okay, so take some Kleinian group. This is some discrete subgroup of PSL to C. So remember, PSL to C is just the group of Möbius transformations as an abstract, as a Lie group. So it is the quotient of the group of 2x2 matrices by the subgroup generated by minus the identity. It is the group of Möbius transformations as an abstract Lie group. Okay, so this is the case. So this is if you take a Kleinian group, this is a discrete subgroup. You can take the quotient, the space of classes of lateral classes of this group is naturally a manifold. It's the same as being discrete, a three-dimensional manifold, because 3 is the dimension of PSL to C. And see, if you have this group, this manifold, then naturally PSL to C, this group of Möbius transformations, acts on this M by multiplication to the right. You take quotient to the left by your group gamma, your discrete subgroup, you can still have multiplication to the right. And it is in this context that we want to ask if this homogeneous space M can be compactified. Okay, so let me just recall some brief things about Kleinian groups. So if you have a discrete subgroup of PSL to C, first it acts on hyperbolic 3 space properly discontinuously, and that is just the fact that it acts by preserving a metric. And you can write, in fact, that as a homogeneous space, H3 is just the quotient of PSL to C by PU2. So this is the unitary group when you have your action of the group of Möbius transformations on hyperbolic 3 space. The stabilizer of a point is the unitary group. Okay? So, and you have also an action on P1, or the Riemann sphere. And this action is not properly discontinuous. There's a partition of your set, of your projective line into 2 sets. One is the limit set, a closed set having the dynamics. And the other is the discontinuity domain. It's an open subset where the group acts properly discontinuously. And in fact, when you have your group, if you divide this discontinuity domain by the action of the group, I'm thinking the group acting to the left, then it is a union of some Riemann surfaces, complex curves, which may or not be compact. So let me draw them like this, and this is a quotient. Okay, so this is Kleinian groups, and these two pictures, H hyperbolic 3 space and the Riemann sphere, can be glued together. You can see, you've seen it, that hyperbolic 3 space may be compactified as a manifold with boundary when you glue the sphere at infinity, the ideal sphere, the endpoints of the hyperbolic geodesics. Your group acts hyperbolically in the inside, conformally on the boundary, and it acts all together. And in fact, you can glue these two actions together, saying that you will have your limit set on the boundary, and then your discrete group will act on the complement of this limit set properly discontinuously, and your quotient will be a manifold with boundary. So in the interior, you will have hyperbolic 3-dimensional geometry. In the boundary, you will have conformal geometry. Okay, so that's the picture. And so this is our Kleinian groups. Okay, this is an image of one of the Kleinian groups I will be thinking about, one kind of, like quasi-Fuchsian groups. And okay, so let me state the result. So you have a Kleinian group. You will find some group that's non-elementary, as we will learn more about elementary groups in the talk by Valdemar. So you take most groups are non-elementary, or we can classify non-elementary groups. So you pick a non-elementary group, and then you have this homogeneous space. This space where PSL2C acts transitively. And the theorem is that the first part is a criterion to decide when does the space admit an equivariant compactification as a manifold. And in fact, your group admits a compactification where the group still acts. This is an equivariant compactification if and only if the group is convex co-compact. It's just one word, convex co-compact, and I will come back to this word later. Okay? So, and the second is, well, if we can compactify while preserving the action, in how many ways can we do it? We can do it in many ways. In these cases where we can do it in many ways, but all of them are related by some sense elementary transformations, and these transformations are the following. So let me read the statement. Any two equivariant compactifications are equivalent up to blowing up invariant curves and blowing down invariant surfaces. So in these manifolds, so let me draw. So we have the homogeneous space here. This is a 3-dimensional manifold. PSL2C acts to the right on this space, and we will compactify this space into some compact 3-dimensional manifold, the manifold with complex manifold, which will non-singular, which will have manifold, which will have still an action of PSL2C, and it will be the same acting by PSL2C and then taking the image, or taking the image and then acting by PSL2C. So in this 3-dimensional manifold that compactifies it, we have one 3-dimensional orbit coming from this 3-dimensional manifold that embeds. But of course, we have more, because we know that we're taking the case where this manifold is not compact, and we have some extra orbits here. So there might be orbits which are essentially the projective line, with this action of PSL2C by Möbius transformations, and we may blow up this curve. This will produce a surface, and we will still have an action because we are blowing up something that is invariant. So these two are different compactifications, they are different manifolds, but they are related by a very simple transformations. And the theorem says that if you produce two compactifications of this homogeneous space, you can go from one to the other, either by blowing up invariant curves, probably finitely many. Probably you have to do the inverse transformation, blow down some surfaces into some curves, but you can connect both of them.
Has
so
negative normal bond automatically, no? The surface, in the case of the surface that you blow down,
there's a criterion there's a criterion that allows you to do it. It's
famous complex analysis.
from the Japanese school. No. Grawit is dimension 1, and the equivalent fiber. This is a fiber case is by the Japanese school of complex analytic geometry. I don't know, but it's an analog of Grauer's theorem. Okay, so there's two parts, and let me tell you about the first one to begin with. So we are given a Kleinian group, and we want to construct a manifold where PSL2C acts, and where this group is the stabilizer of a point. This is equivalent to say, I want to compactify the homogeneous space associated to this subgroup. Okay, so let me do this compactification, and to begin with, let me compactify PSL2C. Okay, so PSL2C, each element of PSL2C can be described by a class of matrices, and what we will do to begin with is to compactify the group. We'll just embed it into complex projective 3 space in this very naive way. So you have four entries in your class of matrices, and you embed it in this way. You take them as homogeneous coordinates for P3, CP3, and of course, if two matrices determine the same class on PSL2C, is because they differ by a sign. But if they differ by a sign, they map to the same point in projective 3 space. So this is well defined. So this is the first thing. We can compactify the PSL2C. And if you think about it, in PSL2C, you have two actions of PSL2C upon itself. The one given by left translations and the one given by right translations. And these two actions extend holomorphically to these compactifications. Okay? So you can say this in other words. You can say that if you take the vector space of 2 by 2 matrices, this is a vector space, 4-dimensional complex vector space. When you remove the zero matrix and you projectify, you get P3. In this P3, you will have some open subset corresponding to non-degenerate matrices,
the complement of the quadric, in fact.
Which is the complement of the quadric. Yes. Okay. So I will repeat what Alberto just said. So we have CP3 here. There is some quadric here, which is, okay, I'll come back to the quadric. Let me call it Q. And in the complement of this quadric, I have something that is the image of PSL2C. Okay? So this is the quadric, and the quadric is given, of course, the image will give me all, here I have that the determinant is non-zero, so AD minus BC is non-zero, so I can never attain the quadric given AD minus BC equals 0. So this is a quadric, and this quadric, as we know, is doubly ruled. It has two rulings. Okay? So let me describe the action, both actions, the action of PSL2C to the left and the action of PSL2C to the right on this P3 by describing, well, the action here, we know what it is. It's just the action by left translations and the action by right translations. But let me tell you what the action on Q looks like. Okay? So this is what I said. The compactification is B equivariant. There are two actions of PSL2C upon itself, one to the left, one to the right, and both get preserved. And moreover, these two actions become actions by projective transformations of P3. Okay? And there's some complement that's a quadric. Okay? So it's doubly ruled. So this quadric is biolomorphic to the product of two projective lines. And so let me make this correspondence explicit. So you have, this is a class of matrices of rank 1. It's a non-zero matrix of rank 1 up to multiplication by a constant, but its image and its kernel are well defined. They are one-dimensional subspaces of C2. Okay, so, and they are rank 1, so this is well defined. Okay, just image and the kernel of the, and when you act to the left, say I multiply to the left by some matrix A, so this is the same as taking the image of this matrix AM and the kernel, or the classes. And of course, if I multiply a matrix to the left, its kernel does not change. So here, the kernel does not change. And in fact, this matrix acts upon the image. So this action to the left acts by Möbius transformations on the first factor and trivially on the second. And the same happens when I act to the right. Okay? So, but in the other factor. Okay? So, in particular, so this is the whole group PSL to C. How does it act on this P3 through this embedding? So in this doubly ruled quadric, which is isomorphic to CP1 times CP1, the left action of PSL to C will act on this first factor and not on the second, and the action to the right will act on the second factor or not on the first. So, in particular, see, if I take the action, if I take gamma, my group in PSL to C, my Kleinian group, I can make it act to the left on this space. Okay, so omega was the discontinuity domain associated to gamma. So this group omega acts through the action to the right, acts on this quadric. It acts trivially here, because the action of the group is trivial. And it acts as it acted before. And the fact that I add a trivial factor where I act trivially doesn't change anything. So my group, gamma, acts to the left upon this space. And the quotient is, well, is the quotient of the first factor times P1. And we just said that this quotient was this union of Riemann surfaces of complex curves. Okay? So see, through the action so if I take gamma, subgroup of PSL to C, it is a discrete subgroup of PSL to C, so it acts properly discontinuously on this part, PSL to C. And it acts properly discontinuously on this part, omega times P1. And in fact, these two actions glue together well. So that's what I said before. So gamma, via the action to the left, acts properly discontinuously on this subset of the quadric. And it also, because it is a discrete subgroup, acts properly discontinuously on the image of PSL to C into this space. And I have this open subset. If I take them together, this U gamma is just P3, where I remove the limit set of the action times P1. Okay, so this group, this open subset U gamma is just removing the lines of one ruling that correspond to the limit set of gamma. And then there's this result that was also obtained by Akira Fujiki, who never published it, around the same time. So you have some discrete subgroup of PSL to C with non-empty discontinuity domain. And so you can define this set, U gamma. And the first thing is that your group acts properly discontinuously on this subset. if your group is convex co-compact, which I haven't said, but I will say what it is in a minute. If your group gamma is convex co-compact, then when you take the quotient by this group, you get a compact manifold. And because we are taking the quotient to the action to the left, we still have the action to the right. And we keep acting by this group. So PSL2C still acts to the right on this manifold. So this is the first part of the theorem. So in this way, if the group satisfies this condition, which I won't tell what it is right now, you get a compact manifold endowed with an action of PSL2C, and there's an orbit that's exactly the quotient of PSL2C to the left by your group gamma. So this is the first part of the theorem. Okay? But in order to say it right, I need to tell you I need to tell you more things about this. So let me tell you something about the first part. Okay? So I have my drawing here. I have an action of PSL2C to the left and an action to the right. And let me quotient by PU2 to the action to the right. Okay? So I have P3. PSL2C, when I quotient to the right by PU2, gives me hyperbolic 3 space. And I have here the doubly ruled quadric, which is P1 times P1. And when I act to the right by U2, this action acts transitively upon the second factor and does not act on the first. So it just kills the second factor. Okay, so the quotient by this action is naturally identified to H3 union P1, which is exactly this drawing. Okay? So this is our different, this is H3. It has the limit set here. This construction works for every Kleinian group. So the fact that this quotient is given by the action of a compact group tells you that the fibers are compact, that the projection is proper, and this in fact implies that if you remove the pre-image of the limit set, then you act properly discontinuously on what's left. Okay, so that's the proof of the first part. And for the second one, I need to tell you what the convex co-compact group is. Maybe I won't. I will just give you two classes of examples of convex co-compact groups. So Schottky groups are convex or compact groups. So you heard Vanessa Alderete's talk yesterday about Schottky groups. And you recall that Schottky groups are these groups that act on P1, that they have two, for example, they have some number of generators, say 2 generators. And they have some this generator G, say, and there's a generator H, and they map the exterior. They come with, for the action on P1, 2 pairs of circles, and they map the exterior of one and the interior of another, and they generate a group. And when you quotient, for example, this one, when you quotient P1, you obtain, because I took 2 generators, a genus 2 surface. And if you consider this action and you extend it to the interior to hyperbolic 3 space, in fact, you get a handle body. You get, when you take the action, not only on P1, but on hyperbolic 3 space and the boundary, and you remove the limit set, what you get is a compact manifold. Okay? So what's important is that for Schottky groups is that when I remove the limit set, which is some Cantor set here, the action, the quotient is compact, the quotient of the interior of H3 and the boundary. Okay, so and you can take that as a definition of convex co-compact groups, Schottky, and also we have co-compact Fuchsian and quasi-Fuchsian groups. So these groups, you know them. So a Fuchsian group is a group acting on the upper, say on the upper half space by Möbius transformations with real coefficients. But in fact, you can see this action as an action on all of the Riemann sphere. You will have, in general, if you take, say, if the action on the upper half plane is a genus 3 surface, then you will act properly discontinuously also in the lower half plane. And the action will be, the quotient will be the mirror image of this, the quotient upstairs, and your limit set will be this line. And once again, if I take the quotient of H3 and of the projective line at infinity, I get a compact manifold with boundary. So what I say is that, see, now that I take this fibration, this, not a fibration, but it's almost a fibration, this proper map, I took the quotient to the left, so I may still act, I took the quotient to the right, so I may still act to the left by the action of gamma. And this action will be compatible with the projection. So if my quotient here, once I remove the limit set, is compact, then the quotient here will be something that fibers with, that has a proper map onto a compact set, so it will be compact as well. So this is a sketch of the second part. Okay, so this is the first part of the theorem, and there are many more convex compact groups. For example, PSL 2Z is not convex compact. And around the year 2000, Lescure proved that you cannot compactify equivariantly the homogeneous space associated to this group. So this is general. So this is a okay. So it's compact if this is. So this is a theorem. Okay. So what we just did, we succeeded in proving this existence of equivariant compactifications, but at the same time, we proved that there are some subgroups of the groups of projective transformations in dimension 3 that act on some open subsets of projective 3 space with compact quotient. Okay? So in particular, this embedding of our group into PGL4C, onto the group of projective transformations of 3-dimensional projective space, makes it a higher dimensional Kleinian group, as defined by Alberto and Pepe, with compact quotient. So these are, we know the classification of these things in dimension 2, and this is a theorem by many people. If you have some infinite group PGL3C, which acts with compact quotient of on some open subset of the projective plane, then it is essentially affine, so it preserves a line, or it is complex hyperbolic, as we learned in the last talk. Okay, so we know very well these groups in dimension acting in dimension 2. But in dimension 3, we do not know them very well. So these are some examples of some groups. So there's no analog of this theorem by Inoue, Kobayashi-Okai, Klingler, and some refinements later by Kano and Seade. So there's no analog in dimension 3. We do not know where to start. We do not know almost anything about these things in dimension 3. And part of the difficult thing is that the manifolds we obtain as quotients fall in the dark side of complex manifolds. They are not scalar, and they have no meromorphic functions at all. Have no globally defined meromorphic functions. So they are in the... So we don't... How can you study some... So it's difficult to study these manifolds because they don't have objects to... They have just this structure, and the structure is not... So we don't know how to give an analog of this theorem in dimension 3. Okay, so... Okay, so let me point at some generalizations of this side of the story of building these groups acting projectively on open subsets of P3 with compact quotients have been developed in Mayra Mendes' thesis, which will... Okay, so I'll talk about a bit of that later. So Mayra is here, so you can ask her later some further developments of this. Okay, so this is the first part of the theorem. The first part was we are giving a discrete subgroup of PSL2C. We construct this three-dimensional manifold where PSL2C acts, and we want to compactify it while preserving the action. So we stated some condition, which is which produces for some groups. So this works. So for convex to compact groups, this produces an equivariant compactification. Okay. So now let me go to the second part of the theorem, and the second part. In the second part, we need to classify these three-dimensional manifolds where PSL2C acts. So suppose you have some manifold M, compact, complex, and then you have a holomorphic action of PSL2C. And suppose that you have some point, and that the point has gamma as stabilizer. So gamma is necessarily some discrete subgroup of your group of Möbius transformations. Okay, so what can we say about M? So according to the theorem, we should be able to modify M by blowing up, blowing down. And then if our group...
The hypothesis that acts with a dense orbit, no? What is it?
No. So it acts...
M can be a dimension higher than 3?
No.
Okay.
It's compact, three-dimensional. And there's an orbit of dimension 3. And the stabilizer is some given subgroup, discrete.
That must be dense.
What?
That orbit must be dense.
Okay, yeah, sure. It's a three-dimensional orbit.
Exactly.
And the complement is an analytic subspace
Of dimension is less than 3.
of dimension less than 3.
Okay.
And we want to understand what's the complement of the orbit in order to classify this, to understand this M. So this is the stabilizer of a point, so that we have this embedding which commutes with the action. Okay, so this is an equivariant compactification as we defined in the beginning, but we know nothing about it, so we need to start understanding it. Okay, so the first thing we can say is that, okay, it is not just, if we only have this orbit, then in fact our group this manifold is supposed to be compact, and there's some orbits extra orbits beyond this three-dimensional orbit, because if not, our group would be co-compact. We will be taking the group associated to a compact hyperbolic manifold, and we're not. So we have, in principle, we have orbits of dimensions 0, 1, and 2 with this three-dimensional orbit. And the first thing is that there are no fixed points. There are no orbits of dimension 0. In fact, there's a theorem by Kuzhmirenko which says that in this case, if PSL to C, which is a simple Lie group acting holomorphically, has a fixed point, then I can find coordinates around this point where the action is linear. It's a linearization theorem. And in fact, PSL to C, its only linear action in dimension 3 is the adjoint action, and this action has two-dimensional orbits exclusively. So you cannot have a three-dimensional orbit and a fixed point. So there are no fixed points. So we only have one-dimensional orbits and two-dimensional orbits. Okay? So surfaces are very well understood. So we may list all the surfaces where our group PSL to C acts holomorphically without fixed points. Okay, so let me draw once again what.
Use Kodaira.
No, we have, you don't need to. You may, but it's very easy because, okay, I'll come back. But you don't need Kodaira in this. Okay, so I have my manifold. Now this is my manifold M, which is compact, three-dimensional. There's some open orbit with stabilizer gamma, and the complement has some complex surfaces. That may be singular, I don't know. You may have lots of connected components. And you do not have fixed points. Okay? You cannot have fixed points. And then you have some surfaces where your group acts, PSL to C acts without fixed points. And we can classify these surfaces. So let me give you the list. Okay? So the first kind of surfaces where PSL to C may act is just you take P1, you take the product with some curve, and you act on the first factor. And you do not act on the second one. Okay? So this is some examples. This has infinitely many one-dimensional orbits, one for each point of C. And this will be important. So this is the first kind of surfaces. So these surfaces sort of look like this. You have one-dimensional orbits gluing together into a surface. The second is you take P1 times P1 and you take the diagonal action, the action by Möbius transformations in each coordinate. Here you have one-dimensional orbit, which is the diagonal. If your two coordinates are equal, then they will remain.
Gamma. No, my gamma beta.
No, gamma.
Gamma.
It's PSL to C that acts, not.
Not independent. Otherwise, it's homogeneous.
Otherwise, it's homogeneous, but it's PSL to C that acts on this. Okay, so this is another one, P1 times P1. And it has one curve. One one-dimensional orbit and one two-dimensional one, which is the complement of the diagonal. You have P2, where PSL to C acts when it's, say, by projectivizing the adjoint representation, P2, and you preserve a conic. Or if you want, you quotient this one by the involution that exchanges the two factors, which commutes with the action, P2. This also has one curve.
The conic.
The conic. The conic. So when PSL2C takes the form of SO3C.
The action of the conic is still canonical to the whole thing.
The whole thing.
By polar.
Yeah. Okay. Okay. So this is another one. Okay. So the next one are what are called Hirzebruch surfaces. Let me tell you how you may construct them. Let me give you one example. You know that PSL2C acts on P1 by Möbius transformations, so it also acts on its tangent space. Okay, its tangent space is a line bundle over P1, and the action extends to this space. And in this space, you have one orbit, which is given by 0 vectors in the tangent space, and the rest is just one orbit. You can take any non-zero vector to any non-zero vector through the action of PSL2C. Further, you may compactify this surface, which is non-compact, by adding a section at infinity. So this would be the second Hirzebruch surface, and it will have one two-dimensional orbit and two curves, two one-dimensional curves. So if you take some tensor powers, you will get the whole family of Hirzebruch surfaces, and they are here. So
every even, you do the same construction for every essentially the same construction for every Hirzebruch surface, no?
Yes.
So you have a rank 2 vectors bundle.
You have no rank. Well, yeah, you can do differently, but let me just give it as a compactification of some
line bundle
of even Chern class on P1. Okay. So okay, and the rest of them, the other ones are homogeneous Hopf surfaces. Let me give you a description again through the tangent space of P1. So you have the 0 section here. And then if I take, for example, some complex number, lambda of modulus different than 1, I may do the following. So you know that if lambda acts, if I take C and I take away 0, and I take the quotient by this number by multiplication, I get an annulus, and then I glue together, and then I get an elliptic curve, a torus. Okay, you know how to do this on C?
Actually, it's the tangent bond is Hopf bond. Has a polymer class 1.
No, but I want PSL2C to act, not SL2C. So I do it in this space, but it's the same. Okay, so I take the tangent space to P1. This has an action by PSL2C. And then I can do fiber by fiber this construction with the same lambda. This action will commute with the action by PSL2C. And at the end, I will find some manifold that is homogeneous under the action of PSL2C that acts on, that has an elliptic fiber bundle over a rational curve, CP1, and it's homogeneous under the action of PSL2C. It has just one two-dimensional orbit, and that's it. Okay, so we have this list of surfaces, and they have some curves in it. And of course, they are embedded in this, they are embedded into this manifold M, but to make the complement of the open orbit. But this embedding may have singularities somewhere around. Anyhow, we know that this singular space should be made of orbits, because it should be invariant under the action. Okay? And we also know that these surfaces, when they, in the place where two of them intersect, they should do so along these one-dimensional curves. Okay? And we control a lot of these curves and a lot more about the topology. So these are the elements, some of the elements that enter into this classification. And there are other elements, and that's sort of the not very fun but very useful part, where you can give normal forms for the vector fields that generate the action in dimension 3. So if you do this carefully, you study the vector fields that come with this action, holomorphic action of PSL2C, you can give a complete classification, and this classification you may see exactly what the action looks like in the neighborhood of some invariant curves. So these invariant curves, we have some numbers that will be typically attached to it, and in fact you can there begin to recognize some things, some invariant curves that need to be blown up. So let me tell you this. So if you have some invariant curves here, these invariant curves have a normal bundle. So in general, they will have the form O of, so these are rational curves. So they will have, you have two integers, lambda 2 and lambda 3, which together sum the normal bundle. And in fact, if this lambda 2 and lambda 3 have the same sign, you should blow up this curve, and it's convenient to do it. So you have a very good criteria on when to blow up. And once you blow up these curves, it turns out that these curves, these surfaces intersect only with normal crossings. So they are sort of reduced. They have no longer singularities, and they have very nice geometric points. And then you have all this combinatorics, like you cannot glue anything with anything because things glue along the invariant curves. Invariant curves. So, for example, and then I told you how the invariant curves are. So, for example, some components will be homogeneous Hopf surfaces because they cannot glue to anything else. And you can have, for example, I have, you can draw a dual graph. And you get, for example, you may have P1 here, and then it has one invariant curve, and then you intersect it with Hirzebruch surfaces that has two invariant curves. You may glue one of the invariant curves to this P1, and the other one to another Hirzebruch surface, and then another one to another Hirzebruch surface, and then another to P2. So, but you cannot do anything. For example, you can prove that this cannot happen, in fact, because there's some orientation that comes from the fact that these two curves in the Hirzebruch surface have opposite self-intersection numbers. So there's a lot of geometry and some combinatorics that come from the topological numbers of the curves in the surface, of the surface in the space. And in fact, if you work together with the information you get with the normal forms from the vector fields, you eventually can distinguish some curves, some surfaces. You can decide that some surfaces need to be collapsed, and once you start collapsing them, you end with one of two situations. Either you have a homogeneous Hopf surface, and then you can conclude that your group was not elementary, or if not, you can transform this manifold M by blowing up and blowing down these curves and surfaces. You can take it to the model we constructed in the first part. So, in particular, our group, gamma, in that case, must be convex compact and non-elementary. So this is a sketch of the proof. And there are some, so I will finish here the sketch of the proof. And let me just tell you a bit about some recent works where these things have, some recent things where these things that have contact with some of these things I have been talking about. So the first is Mayra Mendes' thesis and the article this article that she's writing about complex orthogonal groups in dimension 3, where she constructs more general groups acting on projective 3 space and in some 3-dimensional quadrics having compact quotient. These groups are come into this thing about announced representations have been studied by these people. So there's some contact with this techniques or these themes that Guichard and Wilhart have dealt with. There's, in general, there's a more contact in this work of Guéritaux, Guichard, Cassel, and Minard, which is compactification of some Clifford-Klein forms, so more general spaces, like the one I'm considering, but they consider they can produce compactifications for lots of spaces, preserving some of the geometric features. There's another recent work by Miebach and Olje Klaus about higher dimensional Schottky groups, generalizing work by Laruson and then Seade and Berhovsky, where they recover some of these equivariant compactifications associated to Schottky groups. And the last is my article where all these things are written, but they are written in a way that's sort of difficult to find. So that's why I wanted to tell you what's in it. And that's it. Thank you very much.
¿Questions? Sí. Lo hiciste muy bonito, ¿eh?
Gracias.
Creo que es la tercera vez que lo oigo, pero cada vez lo entiendo más.
Perfecto. Muy bien. No te canses.
Pero siempre hay algo. Pero, a ver, creo que ya te había hecho esta pregunta y ya me la había respondido. Yo me acuerdo de la respuesta. ¿Qué pasa si en lugar de PSL2C tomas PSLNC? Tienes algo análogo, ¿no? Tienes un grupo que actúa.
The key part here is the thing that makes in the first part. The thing that makes things work is that you construct a B-equivariant compactification of your group. In fact, you can prove using the same methods that this B-equivariant compactification is unique. And this unicity is somehow related to the fact that you can quotient to the right and then add to the left. And so this is essential. So in general, you can always compactify as... so you can okay. So this is the first thing that happens. And the other one is that what's left was very simple to understand. Was just one quadric, two actions. So, okay.
Let's say 3 by 3. Let's say PSL3C. Therefore, you have a cubic.
You have a cubic given by the determinant.
It's most probably singular because that's
it's very probably singular, and it will have orbits of different dimensions.
Different dimensions, but still, I mean, you can blow up, blow down. I mean.
So yes, you can do it, but you need to understand this this 7-dimensional variety given by the determinant. It's fibered. It is singular, and in general, you will not. The condition for a group to act on open subsets of this will be very, very restrictive.
Very but you can blow up and suppose that a cubic is non-singular.
But then you lose the action to the other side.
Why does it work like that? Why? I think you have the same thing, no?
Well, okay, you have the same thing, but there are a few examples. Let me say, I think that there are very few examples of groups where you will have compact quotients. Okay. And for the second part, it's a sequence of low-dimensional miracles that make this work. So there's not you cannot. So there's at each point there's a miracle that barely makes it happen, and then. So.
Let's take Adolfo.
Muy bonito, ¿eh?
Gracias.
We have 20 minutes.